Example 3 for 310. Compare the values of delta y and dy if y equals f of x is this polynomial function x cubed plus x squared minus 2x plus 1, and x changes from 2 to 2.05 and from 2 to 2.01. Alright, so let's just take a look at this. So first of all, if we just do delta y, okay, we've all taken physics, right? Yeah, physics. Alright, and well, if you haven't taken physics, that's a good physics notation there. Delta y, that means change in y. What's the change in y? How much did y change? Alright? So if we look at part A, we're going from 2 to 2.05. This is x. It says x changes. So x changes from 2 to 2.05. So if I do f of 2 equals something and f of 2.05 equals something, how can I determine f of 2 and f of 2.05? Substitute them into the equation. I don't want to do 2.05 to the third power and so on and so forth. So I'm going to just type my equation in here. So I'll x cubed x caret 3 plus x squared minus 2x plus 1. And I verify I typed it incorrectly, and I did. Go over to my table, and the numbers I want are 2 and 2.05. That gets me 9 and 9.717625. We'll go all decimal places since there's a terminating decimal there. 9.717625, and we have 9. Okay, so looking at part A, they want me to find delta y. All right, what is delta x?
0.7176.
What's delta x?
The change in x.
The change in x, and what's x changing from and to?
2 to
2. So how much did x change?
2.05.
0.05. So to find change, you subtract, right? So if I'm going from 2 to 2.05, delta x was 0.05. All right, that might be necessary in a little bit. Bless you. All right. If I want to find delta y, these are the y values, right? 9 and 9.717625. So delta y in that situation is 0.717625, right? Then we're going to compare the values of delta y and dy. Okay, so there's delta y for part A. All right. Now, as far as dy is concerned, okay, dy is called a differential. You already have every skill necessary to do differentials. Okay, everything there is to do with differentials, you already know how to do. Because for this entire chapter, we've been differentiating, right? Typically with respect to x, most recently with related rates, we differentiate with respect to t, that kind of thing. We did y prime, f prime of x, all this kind of stuff, right? All right, all a differential is the derivative of each term with d whatever letter you're differentiating next to it. That's all it is. So if I'm differentiating a y term, I put a dy next to it. If I'm differentiating z, dz, theta, d theta, q, dq, Dairy Queen, good ice cream. But the point is, d whatever, so that's differential. So if I'm looking at y equals x cubed plus x squared minus 2x plus 1, what type of function is that?
Quadratic.
Not quadratic, polynomial. Quadratic would be second power. That's a specific. It's kind of like a quadrilateral is four-sided figure, but a square is a specific four-sided figure. A quadratic is a specific type of polynomial. This is actually cubic if you want to get really technical, it's to the third power. But polynomial function. X is raised to powers, right? And y raised to a power. Everything's just a power structure. So the derivative of y is 1, right? And I put a dy next to it. Derivative of x cubed is 3x squared, and guess what I put next to it?
No.
Dx. Every letter you have. If you differentiate, just put d that letter next to it. All right, continuing on. Derivative of x squared is 2x, and I'm going to put dx. Derivative of negative 2x is negative 2. I'm going to put a dx. Derivative of 1 is 0. I'm just going to leave it blank. That's how you do a differential. You differentiate each term, whatever letter is in the term, d that letter that goes next to it. That's it. Okay. Dx is going to be approximately delta x, and dy is supposed to be approximately delta y. They're not exactly the same thing, but they're pretty close. Close enough that we're going to say they're interchangeable. So looking back over there, if I want to compare the values of dy and delta y, I just figured out what delta y was for 2 to 2.05, right? I'm going to let delta x approximate the value of dx, okay? And then x is going to equal what we start at. So I've got a 0.05 delta x. We started at 2 and we applied a delta x of 0.05 here, right? So in the case of this, if I want to evaluate dy, I'm going to let x equal the start. We're going from something, so that's what x equals, whatever. If it says from dog, x equals dog. If it says from 16, x equals 16. Whatever it says from, that's what x is. And then delta x is how much bigger the next number is. So we're going from 2 to 2.05, so delta x is 0.05. So that's dx actually. We're going to make dx and delta x approximately equal to each other, so we're going to say they're interchangeable. Looking at this differential that we've created here, x's and dx's are all over the place, right? There's the x's, there's the dx's. I'm going to replace these two numbers in for all those x's and dx's there to figure out dy. So dy is going to equal 3x squared dx plus 2x dx minus 2 dx. Now before I start evaluating this, what should I expect this to be close to?
0.71765.
Exactly, 0.71765. dy is supposed to be approximately the same as delta y, right? We just figured out delta y exactly. So this should be pretty close to 0.717625. So it's just a matter of typing all that in my calculator, or I suppose I could do it in my head if I really felt like taxing my brain a little bit, but I'm just going to do a calculator. So 3 times 4 is 12 times 0.05 plus 2 times 2 is 4 times 0.05 minus 2 times 0.05 comes out to 0.7. dy equals 0.7. Okay, so compare the values. The whole idea here is you're supposed to see they're pretty close to each other. That's the comparison you're supposed to get. They're pretty close to each other. All right. The reason why we want them to be close to each other is because it can be challenging to do this here. Okay, in some of the problems we're going to see, it's going to be challenging to do this here. And some of the numbers we get are going to be pretty ugly, where it's going to be less challenging to do this here, to actually just differentiate, find a differential, and substitute a couple numbers in to evaluate like that. All right. And to be honest, that gets us pretty close. We'll call it close enough. We're not building bridges today, so we should be good. All right. So that is what they want us to do there. So the other part of this problem is just do the same thing. Just go from 2 to 2.01. So let's see if I can get all this stuff in over here. Oops. Wrong one. Shrink up there. That. Perfect. Okay. So we're going to do part B now. We're going from 2 to 2.01. All right. So first off, if I want to do delta y, I'm going to go part B. I want to know f of 2, which still equals 9, right? And I want to also know f of 2.01. Okay. And f of 2.01, again, my calculator knows that. I've still got the thing typed in, so I can just come over here. 2.01. That comes out to 9.140701. Which tells me that the delta y in this case is going to be this minus this, so 0.140701. Just like that, we find delta y. All right? So once I know what delta y is, I want to find out what dy is. So, Renee, what is x?
2.
And what's delta x?
0.01.
Perfect, 0.01. We're going from 2, so x equals 2. We're going up to 2.01, which is a change of 0.01. So just like that, we got x and delta x. But again, we're going to make delta x actually dx for our purposes. And we're going to pretend they're the same, even though they're not quite. All right? And the differential hasn't changed. It's still this thing here, right? So if I want to find dy, I'm simply going to do 3x squared. That would be 3 times 4 times dx, 0.01, plus 2 times x, which is 2, times dx, which is 0.01, minus 2 times dx, which is 0.01. And just like that, I've got all the stuff I need to find what dy is this case. So it's going to be 3 times 4, which is 12 times 0.01, plus 4 times 0.01, minus 2 times 0.01. Comes out to 0.14. Okay. Now, comparison again, they're pretty close, right? Now, I want you to get a second comparison between the two problems, the blue and the red problem, because this is going to be important in this situation. All right? Which one's closer to the right answer, I mean, as far as comparison is concerned? Is this or this closer to each other?
Red.
The red's closer to each other, right? What's different between the red and the blue?
How far apart from 2 they are?
How far apart? So the delta x here is smaller, and the discrepancy in delta y and dy is smaller, right? That's going to be a key to these problems. The closer you are to the actual point of interest, the smaller the delta x is, or in this case dx is, the more accurate the comparison between these two numbers is going to be. So one thing with differentials is there's an understanding when you use differentials that you're going to get really, really close to the number. The dx is going to be very tiny. The tinier dx is, the tinier discrepancy between dy and delta y is going to be. All right? And the further away from x you get, the more error there's going to be. All right? So that's the key to these problems is we're looking for really close to decrease error. Because again, they're not equal. They're never going to be equal. But they're going to be really close to being equal. And the closer you get x to delta x, you know, the closer you get that change in x to be, the more accurate this comparison is going to be. And that's kind of one of the goals of this section here, is to get really close to increase accuracy.